Hello everyone, this is Manohar Reddy, Institute of Aeronautical Engineering, Department of Cybersecurity. Today I am going to discuss about the next concept is generator matrix. So concept of generator matrix. The concept of generator matrix is derived from coding theory. So coding theory we already discussed in different point of view. So different types of codes will be generated, and that codes are generated by the term called as generator matrix. So to know about the generator matrix, we are going to know about some different terms. So those are nothing but Galois field and generator matrix and the parity check matrix. So in the previous sessions we already discussed about the different algebraic structures called as groups, rings, fields and everything. So to know in detail about generator matrix, we must and should recall this Galois field concept. So Galois field concept we already discussed in the linear algebraic structures. So this is also, you can pronounce it as Galois field. Galois field. So generally what is meant by field or what is meant by algebraic structure? So algebraic structures obviously performs operations on the different types of numbers or different types of equations. So same that Galois field, a field F is set of elements with two operations called as additions and multiplication, two operations plus and multiplications, and that satisfying the following properties. That should be satisfies the following properties. That following properties are different types of properties. One is commutative property, another one is associativity property, another one is distributive property, and identity property and inverse property. Identity property as well as inverse property. So this is inverse property and this is identity property, and this commutative property, associativity property, distributive property. So a field F is said to be if and only if a plus and multiplication operations performs based on the different rules. That rules are said to be the laws: commutative law, associative law, distributive law, and identity law, inverse law. So if it satisfies all these properties, then you can say that it is a field. Right? So F is a closed under plus, and there is A plus B and A dot B are in F. So commutative law property is what? A plus B equals to B plus A, or A dot B equals to B dot A. And similarly, associative law. So A plus B of plus C equals to A plus of B plus C, or A dot of B dot C equals to A dot of B dot C. And similarly, distributive law. So A dot of B plus C equals to A dot B plus A dot C. Further, identity elements 0 and 1 must exist in a following satisfied. So A plus 0 equals to A. 0 is the identity element with respect to plus operation. And similarly, A dot 1 equals to A, where 1 is the identity element with respect to star operator. Star or dot, you can write anything, star or dot operator. For any A in F, there exists an additive universe. A plus of minus A equals to 0. So here the minus A is inverse element to this A with respect to the plus operator. Minus A is inverse element to this A with respect to the addition operation. And similarly, A into A inverse equals to 1. So A inverse is the inverse operation to this A with respect to the dot operator. With respect to dot operator. So the above properties are true for fields with both finite as well as infinite elements. So if any algebraic structure satisfies all the above properties, then it is said to be the field. It is said to be the field, and which contains a finite elements and which contain infinite elements, but not null elements. A field with a finite number of elements is called as Galois field, and it is denoted by GF of Q. The above properties are all said to be a field if and only if it is a finite or infinite. But a field with a finite number of elements, say Q, is called a Galois field, and it is denoted by GF of Q. So a field contains number of elements is called as Galois field, and it is denoted by GF of Q. If only the first 7 properties are satisfied, then it is called a ring. So this is the way you can understand the concept of field. So why we are talking about this, all the fields means to generate the different types of codes. To generate the different types of codes from generator matrix, we must and should follow this Galois field rules. So how we are going to follow all this, we'll see. So in the bit sequence, we can see here, these are all the code words. 00 and 0101, 1010 and 1111. These are all, you can say that it is a code words. We already discussed in the previous session what is meant by code, what is meant by code words, what is meant by block of code, and what is meant by a repeat code, right? So what is meant by code? Actually, a code contains alphabets. If any alphabet is repeated, then that code is said to be a repeat code. And if the same type of the repeated numbers, repeated alphabets, then it is said to be a block of codes. So the repeated ones, these are all 001, 01 and 10 and 11. These are all, you can say that information bits. But these are all having a repeated ones. So 00 is again repeated 00, and 01 is again repeated 01, and 10 is again repeated 10, and 11 is again repeated 11. So that means these are all having the repeated words, the repeat code. We can say that repeated codes having the same type, repeated codes having the same types, so that you can say that it is a code words. So from this Galois field, we can rewrite it as a k equals to 2 and n equals to 4 from this point of view. That means the code is what? 4, 2 code. It is said to be, it is a 4, 2 code. So 4, 2 code is nothing but, you can write GF of 2 power 4. The number of elements in the field following all the properties, then it is said to be field. So that is what we written previous slides, right? So 2 power 4 equals to 16 possible words we have to derive from that. And that means GF of 2 power 4 chosen a subset. So 2 power 4 generates 16 bits, right? Among that all the 16 bits, we can take one subset is 000, 0101, 1010 and 1111. So this is one subset of the code word we chosen from all these 16 possible words. We have chosen only one subset from this all the 16 possible words, right? So now we will see what is meant by generator matrix, etc. So what is meant by generator matrix? So generator matrix. A generator matrix is a representation of both rows and columns. So definitely you can say that any matrix formation is nothing but it contains rows and columns. So generator matrix is also having the same rows and columns. And any code C represents code word or code, and it is a subspace of GF of q power n. So in the previous slide only we'll see this. So 2 power 4 equals to 16 possible code words, and this is the generated code word from this all the 16 possible words. So how we are going to generate means we are from generator matrix. So this is the subspace of gf of qn, q power n. So any set of basic vectors can be used to generate the code space. So to generate the code space, we use these basic vectors, right? That is zeros and ones. And we can therefore define a generator matrix G, the rows of which form the basis vectors of the subspace. Basis vectors of the subspace. Definitely it is going to be derived one subspace from all the possible words. So the row of G will be is said to be linearly independent. Linearly independent. The rows are having the same or dependent. Those are not having the same or dependent. So that means they are linearly independent. Thus, a linear combination of the rows can be used to generate the code words of C. So linear combination of the rows can be used to generate the code words. So that is what we derived here. These are all the generated code words from these possible all the words. So among these all the possible 16 code words, we are choosing only one subset. That is what we noted here in this point. And the generator matrix will be a k into n matrix, as previously we said that, with the rank k. So the rank is nothing but among that all the words. We'll say that rank k. And since the choice of the basic vectors is not unique, and the generator matrix is not unique for the given linear code. That means they are not having the same, or they are not having the dependence. That's why we are mentioning that the rows of G will be linearly independent. So from all these points, we can say that generator matrix is one a k into n matrix which contains the rank k, and it contains the linear combination of the rows, and our rows cannot be having the linearly dependent values. So the generator matrix converts or encodes a vector of length k to vector of length n. So from length of the vector k to length of the vector n. So it is going to be transforming. Or converting. So let the input vector be represented by I. So I is represented input vector, and the coded symbols will be given by C equals to ij. So this is the generated code word C, and I is the input vector, and Z is the generator matrix. So from this generator matrix, with the information bit or input vector, we are going to generate new code words. So as per this generator matrix definition, we are going to generate new code words. That is reproduced codes with the help of this generator matrix. So where C is called the code word and I is called the information word. And the generator matrix provides a concise and efficient way of representing linear block codes. We'll see. So how you are going to generate a code words with the help of this generator matrix. We'll see in this example. So consider a generator matrix G equals to 1, 0, 1 and 0, 1, 0. So this is nothing but you can say that 3, 2 matrix, and these 3 rows and these 2 columns we will having. So 3, 2 matrix, and so what we need to get actually, so C equals to ij. With the help of this formation, with the help of this formula, we are going to get some codes. So how we are going to get the codes? So From this formula, I equals to what? Information bits. I equals to what? Information bits, or you can say that it is a input vector. So input vector means they can have 0 0, 0 1, 1 0 and 1 1. So this is nothing but input vector or information bits, you can say that. So from this point of view, you can multiply this input vector with the help of generator matrix. With the help of generator matrix. See here. So first one, C1 equals to 0 0. This is I and this is J. This is G. This is I. This is G. So from this point of view, what is the C1 value? So how we are getting from this value? See here. So 0 into 1, 0 into 1 plus 0 into 0. And next second one, 0 into 0, 0 into 0 plus 0 into 1, 0 into 1. Again 0 into 1, 0 into 1 plus 0 into 0. And similarly, you can write 0 into, this is the way you can write. So 0 into 1 is nothing but 0 plus 0 into 0, 0. And again 0 into 0 is nothing but 0 plus 0 into 1, 0. And similarly 0 into 1 is nothing but 0 plus 0 into 0 is nothing but 0. So totally we will get the code word is 0 0 0. This is the new code word, new code which we generated from this generator matrix with the help of input vector or information bit. So with this we are generating new code word, that is C1. That is C1. And similarly you can see for the C2 also. You can see C2 also. So how we are going to generate? So see 0 into 1 plus 1 into 0, 1 into 0. Similarly 0 into 0, 0 into 0 plus 1 into 1. And similarly 0 into 1 plus 1 into 0. Right? So see how we are getting. So from this point of view, 0 into 1 is nothing but 0 plus 1 into 0, 0. And here 0 into 0 plus 0 plus 1 into 1, 1. And 1 into 0, 0 plus 1 into 0, 0. So finally you will get 0, 1, 0. So this is what we will get a code from this generator matrix with the help of this information bit. With the help of this information bit. And similarly for the C3 also. So 1 into 1, 1 into 1 plus 0 into 0, 1 into 0 plus 0 into 1, 1 into 1 plus 0 into 0. So what will you get? 1 into 1 plus 0 into 0, 1 plus 0, here 0 plus 0, here 1 plus 0. So total you will get 1, 0, 1. And this is the third one. This is the third one, C3, the code which is generated from the generator matrix. And similarly for C1, C4 also. 1 into 1 plus 1 into 0. And similarly 1 into 0 plus 1 into 1. And similarly 1 into 1 plus 1 into 0. So from this whole point of view, 1 into 1 is nothing but 1 plus 0, 0 plus 1 and 1 plus 0. So finally what we will get? 1, 1, 1. So this is the generated code word from this generator matrix. So by seeing this all the scenario, we can say that the generator matrix are used to produce the code words, with the help of this input vector called as information bit. So C equals to IG. So where the C is nothing but produced code or generated code. You can say that produced code or generated code. And I is nothing but input vector or information bit. And G is nothing but generator matrix that will take any of the matrix, not only 1 0 1 0 1 0. You can take 0 0 or 1 0 or 1 1 or 1 anything you can take generator matrix. But in the real time, the generator matrix is associated with the information bit. The generator matrix is associated with the information bit and produce new generated code. That new generated code is nothing but C. So this is the way you can understand this. generator matrix. So from the above generator matrix generates the code is what C equals to 000 and C equals to 1010. This is nothing but C1 and this is nothing but C2, this is nothing but C3 and this is nothing but C4. So we observe that Z equals to 101010. This is 3, 2 code as we discussed in the previous code from the fact that dimension of the generator matrix is 3 into 2. 3 into 2. So from this point of view, like the way you can see another example also. Suppose you can take a generator matrix contain the values are like 0, 1, 1 or 1, 0, 1 or 1, 1, 0. So if it is going to be performing, we can have to take 3 values. We can have to take 3 values. So like the way you have to take 0, 1, 1, 1, 0, 1, 1, 1, 0. So this is generator matrix and this is the information bit. This is the information bit. You need to add C1 to C8 up to C1 to C8. C1 to C8 you need to update it. You need to add. So with this all you need to add 0 into 0 plus 0 into 0, 1 plus 0 into 1. So like the way you need to add up to C1 to C8. Because these bits are contained 2 power 3, right? 2 power 3 is nothing but 8 factors. So 8 factors you need to get. So from these 8 factors you will get all the 8 code. So 8 code words you need to get. So from this 2 power 2, 4 you need to get only 1. That is nothing but 1 code from 2 power 4 scenarios. Right? So this is the way you can understand generator matrix. And next one is parity check matrix. So parity check matrix. So the matrix which is used to detect valid code word using matrix based is a parity check matrix. So parity check matrix is also a representation of the matrix, contains rows and columns, but it is going to validate the code words. Validate the code words generated by generator matrix. Validate the code words generated by generator matrix. So generator matrix is used to generate the code words with the help of C equals to IG formula, where I equals to input vector or information bit and G equals to generator matrix. With the help of C equals to IJ, we are getting some different types of codes, that is code words. But we have doubt that they are valid code words or not. So that is what we have doubt. So whether it is valid code word, so parity check matrix will decide whether it is valid code word or not valid. Parity check matrix will decide. So how it will decide? The parity check matrix is used to detect the valid code words based on the size of the parity check matrix, and if it gets CH transpose equals to 0, CH transpose equals to 0, then you can say that the valid code word, then you can say that the generated code words is valid, right? So if the multiplication of the received word with the transpose of H to be the non-zero vector, it implies that error has occurred. So if CH transpose equals to 0 means the code, generated code is valid code word. But the multiplication of received word, the transpose of H to be the non-zero vector, that means CH transpose equals to non-zero vector, it implies the error has occurred. It implies that error has occurred. So where C is a valid code word and that C is nothing but IG. Therefore you can rewrite CH transpose is IGHT. So from this all the points you can say that only two things. What? So parity check matrix is going to validate the codes, validate the code words generated by generator matrix. That validated code words are validated in which case when it is IGH transpose equals to 0 case, or you can write CH transpose equals to 0 case. So in this case you are going to say that the parity check matrix detects that valid code word and it is a valid code word, and if and only if it is not equals to 0, then it is said that somewhere error has occurred, somewhere the error has occurred. So C H transpose is not equals to 0 means some error has occurred. But C H transpose equals to 0 means it is validated code word. It is validated code word. So for this, hold true for all valid code words, we must have G H transpose equals to 0. That means we need to get that one. So we'll see. Suppose the generator matrix is represented in systematic form is GIP. This is nothing but a standard form or systematic form of the generator matrix formation. G equals to I or P. So that is the systematic form or standard form for the generator matrix. Where matrix P is called coefficient matrix. Matrix P is called coefficient matrix. Then the parity check matrix will be defined as. So this is the formula that where you can say that it is a parity check matrix. So this formation is going to be say that it is a parity check matrix. So what is meant by? So what it is, H equals to minus P transpose or I, minus P transpose or I. So where P transpose represents the transpose of a matrix P, where P is nothing but coefficient matrix, coefficient matrix. So this is because GH transpose equals to I or P or minus Pi equals to 0. So this is what, if we'll get the value is 0 from this formation, we'll get value is 0, then the generated code word is valid. The generated code word is valid. If we are not having this 0 equals to, that means not equals to 0, then you can say that it is a error has occurred. You can say that some error has occurred. Some error has occurred. Right? So this is the way you can understand from this parity check matrix. And see here one example. So for 7, 4 is a linear block code. The generator matrix is given by here. The generator matrix is nothing but here 4, 3, 7, total 7, 4. So 7 rows and 4 columns. So 7, 4 is the linear block code size. This is right. So from this matrix, the matrix P is given by, so the matrix P. So this is I matrix and this is P matrix. So G equals to I or P. This is the systematic form. This is the systematic form they given. Systematic form or standard form, you can see that. So from this point of view, so what is the value of P? 101. So this is all, you can say that it is a P value. Right, so P equals to 101 and 111 and 010 and 010. This is the P value from this generator matrix standard form. So we'll see how we are going to say that. And the P transpose. So from this P value, what is the value of P transpose? So transpose is nothing but we can interchange the rows and columns. You can interchange the rows and columns. So see 1 1 0 0 and 0 1 1 1 and 1 1 0 0. So this is the P transpose matrix. This is the P transpose matrix. Right. So see here what we'll get actually. So this is 1 1 0 0, 0 1 1 1 and 1 1 0 0. So now we observe that the fact -1 equals to 1 for the case of binary. So hence we can write the parity check matrix as what? H equals to minus P transpose of I, minus P transpose of I. So we need to write the generator matrix form into this way. So see H equals to minus P transpose what? 1 1 0 0, 0 1 1 and 1 1 0. So this is all you can say that P transpose. This is all you can say that P transpose. So -1 is nothing but 1 only, so that you can rewrite this one as like this. And this I is 1 0 0, 0 1 0 and 0 0 1. 1 0 0, 0 1 0 and 0 0 1. So now we obtain this H equals to minus P transpose I, minus P transpose I. So that is the way you can understand this parity check matrix. Parity check matrix. So finally we obtain this formation, that is nothing but H transpose equals to CH transpose equals to 0. Definitely we achieved this one. We achieved this one from this formation. So hence it is said to be the parity check matrix. The codes are valid. The codes are valid. Right. So that is way you can understand. And the next one is what? So Hamming distance. So we already said that a code having the alphabets, and repeat code can have the repetition of the alphabets, and code blocks, block of codes, you can say that block of codes are the same type of the repeated codes, So see here, a code with code words, of length n, made up of from an alphabet of size k, then the elements of v of n comma k are called words. So obviously, so 1 2 3 or a b c or bb, anything you can take that is a code, or that is nothing but word. So these are all examples you can write: 0 0 1 1 1 0, and here 1 0 1 1 0 0. So this is all nothing but 6 comma 6 digits, or 6 comma 6 bits. 6 comma 6 bits. So they are denoting the size of the matrix, and they are denoting the length of the matrix. So suppose you can write like 1 0 1 1 0 0 0 1 0 1 0 0. So if you write like this, so this is all the code words you can write. This is all you can write as a code words, and these are nothing but v of 6 comma 6 matrix. V of 6 comma 6 matrix. So these are all you can say that words. And from these words, what we are going to do, what is meant by Hamming distance? So generally Hamming distance is nothing but, so the network signal is low, and it is going to interrupt the transmission medium to do not transfer the data to the destination. So at the time the signal barrier indicates some network signal is interrupted. So at the time we are going to generate some codes. So to generating that codes, we are going to identify the Hamming distance. That Hamming distance is nothing but, so Hamming distance between two words in this v of n comma k. That means you can write the number of places in which they differ. The number of places in which they differ. So that means the given code words, how many places the number of bits are differ. So consider these two words. Here 0 0 1 1 1 0. This is one word, and 1 0 1 1 0 0 is another word. Having the distance is 2. Hamming distance is 2. Why? We already said that Hamming distance between two words is the number of places in which they differ. Number of places. That means from 0, this is 1, until this one is 1 place it is differed, and from 0 is 0 same, and 1 is 1 same, and here 1 is 1 same, and here 1 is differed with 0, and last 0 is 0, right? So that means totally we are having two places differ. They got differed. So this 2 is the Hamming distance. Similarly, you can say that one more example. The code word is v of 4 comma 4 is 0 comma 1 comma 2 comma 3 and 1 comma 1 comma 2 comma 2. So from this example, so 0 comma 1, this place is differed, and 1 1 is okay, and 2 2 is also okay, and 3 comma 2 is also differed. So these two places are differed for these code words, these two words. So the number of places that they differ is called as Hamming distance. The number of places that were differ is called as Hamming distance, right? So from these two examples, we know that Hamming distance is nothing but number of places they differ from the given word. Number of places that differ from the code word. So that is what. And similarly, we are going to find the minimum distance. So minimum distance of a code C, minimum distance of a code C is the smallest distance between any pair of distinct code words. So smallest distance. So when you are taking the number of bits, whichever the distinct pair contains, having the smallest distance. The smallest distance between any pair of distinct code words is called as minimum distance. Minimum distance. So if it is a minimum distance of code that measures a code's error correcting capabilities. Code's error correcting capabilities. Code's error correcting capabilities. So see here we have 5 comma 4. So we can write as this formation 0 0 0 0, and this is 1 0, and next 1 1 1 1, and next 2 2 2 2, and next 3 3 3 3. So this is all. You can say that we have 5 comma 4, 5 comma 4 matrix, right? Okay, so this is one code word, 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 right? So when you are taking Hamming distance for these two code words, obviously you can say that 5, because all the places were differ, right? So all the places were differ, so that Hamming distance is 5. But minimum distance is what? Minimum distance is also, see here, if 0 wants to move the position to this one, if 0 wants to move the positions to this place, it wants to move this place, it wants to move this place, and it wants to move this place, and similarly it wants to move this place and also to this place, also to this place. So then it is said to be for the 0 0 0 0, it is the minimum distance is 5. And next for 1 also same. From 1 also, if it wants to become 2, it moves to this place, it moves to this place, and it moves to this place, it moves to this place, and again to this place. So hence this is called, if this place is called as 5, that is nothing but minimum distance. Minimum distance of the code words 0 0 0 and 1 1 1 and 2 2 2 and 3 3 3. So the code detects 4 or fewer errors and corrects 2 or fewer errors we have seen. That means the previous all the places it is taking as a errors, and they can rectify them as 2 or more errors. So that is what we mentioned from this, all the points. And last one, weight of a code, weight of a word. So generally word is nothing but having, this is word, right? So 0 1 3 and 0 1 5. So this is all, you can say that one word. So but what we need to find, weight of a word. The weight of a word is referred to the number of non-zero components in the word. Number of non-zero components in the word. So this is all one word. So from this word, what we can find, weight of the word. So what is meant by weight of the word? The number of non-zero words, number of non-zero components in the word. So this is one place, number of this is one 0 occurs, this is one number of non-zero place, this is one number of non-zero place, and this is also number of non-zero place, and this is the number of non-zero place. So totally 4 non-zero places will occur. Totally 4 non-zero places will occur. Hence we can say that the weight of a matrix is, weight of a word is 4. Weight of a word is 4. That means we should tell that the number of non-zero elements in the word is become a weight of a word. The number of non-zero components, of the word is called as weight of a word. So that is way we can understand this Hamming distance, minimum distance, and the weight of a word. So we will see one example. We will take one example like, so suppose you can have 2 code words like 0 0 1 2 3 and 5. So this is one code word, and another one is what, 1 2 0 4 5. So this is one code word. So this is code word 1 and this is code word 2. So from these two code words, we need to find Hamming distance and we need to find minimum distance. So what is meant by Hamming distance actually? So having distance is nothing but the number of places that were differ. The number of places that were differ. So the size of the word is having same. C1 equals to C2 equals to 5. C1 equals to C2 equals to 5. Okay, but the having distance is what? We need to know that number of non-zero places. Number of non-zero places. Number of places that differ. Number of places that differ. See, from C1, 0 is here. But here 1, so it is differed, and here 1, so here 2, but it is also differed, and here 2, here 0, so it is also differed, and here 3, here 4, and it is also differed, and here 5, and here also 5. So this is not differ, so it is having same place. So we can say that the number of places that were differ are 4. So from this C1 and C2, the having distance between these two codes is what? 4. Having distance between these two code words are 4. And similarly, minimum distance. So what is the minimum distance? So minimum distance is what? So we need to find out. So 0, 1, 2, 4, 5. Here 2, 1, 0, 4, 5. So the moment of the places that were differ. So 0 wants to become here. So how many places that were differ? 1, 2, 3, 4, 5. So total of 5. And similarly for 1, so 1 wants to 1, 2, 3 place 4, and this is the 5. So for 1 also 5, and for 2, so 1, 2, 3. So that this is the third one. So for the 2, the minimum distance is 3 only. For the 2 code word, the minimum distance is 3. And for the 4, this is 1, 2, 3, 4, 5. So for the 4, you need to have the distance is 4. So like the way the minimum distance we have to find here. Minimum distance is finding like this. And the last one is what? Weight of your word. So this is C1, and C1 is 0, 1, 2, 4, 5 is 1, and C2 is what? 1, 2, 1, 0, 4, 5. So from these two, the C1 equals to C2 equals to the weight of a code word is what? Number of non-zero elements. How many are there? So here 4, and here also 4, right? So the 4 is the weight of your word. Weight of your word is number of non-zero elements in the word, so that the weight of your word is 4 from these two words, right? So this is the way you can understand having distance, minimum distance, and the weight of your word. Weight of your word. So this is all about having distance, minimum distance, and the weight of your word, and the generator matrix and the parity check matrix. So generator matrix are used to generate the code words, and the parity check matrix are used to validate the code words generated by the generator matrix. How can we say that it is a validated code or not? If it is displaying, if it is forming like a CH transpose equals to 0, then the code word is said to be valid. If CH transpose not equals to 0, then it is said to be somewhere error has occurred. That means indirectly the code words are not valid. So this is what we completed in this presentation. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.